The United States is building its future at a scale few people truly understand. Across deserts and forgotten industrial corridors, 100 megaprojects are rising at the same time, reshaping how America competes in the world. In this documentary, we uncover the biggest projects under construction in 2026 and reveal the hidden ambition behind the country's most expensive transformation. Beneath some of the most congested streets in Los Angeles, the LA Metro D-Line extension, Section 1, is the underground transit project intended to deliver one of the city's most important rail expansions of the mid-2020s. For a video about United States megaprojects completing in 2026, this segment matters because it represents the final stage of transforming years of tunneling and station construction into an operating subway link. Section 1 extends the D-Line west from its former terminus at Wilshire/Weston to new stations at Wilshire/La Brea, Wilshire/Fairfax, and Wilshire/La Cienega. This first section is the opening piece of a much larger corridor expansion designed to push heavy rail farther through the Wilshire Corridor, one of the densest employment and destination corridors in Southern California. Its value is not only in adding track mileage, it creates new direct subway access to major cultural, commercial, and residential districts while reducing dependence on slow surface traffic along Wilshire Boulevard. That makes Section 1 a foundational part of a broader network change rather than a standalone line. The most significant construction already involved tunnel boring, cross passages, station excavation, concrete structural work, and the build-out of underground platforms and circulation areas. By the final approach to completion, the work shifts away from excavation and toward railway systems and passenger facilities. In a 2026 completion context, the critical construction activities are the finishing of station interiors, installation and testing of elevators and escalators, completion of ventilation and fire life safety systems, traction power energization, track and third rail finishing, signal integration, communication systems, fare equipment, and the final architectural treatment of entrances and public-facing spaces. Another major task in the completion phase is systems commissioning. For a subway extension, the project is not complete when the tunnels and stations are physically built. Metro and contractors must test train control systems, verify emergency procedures, integrate power and communications, certify ventilation performance, and run trial operations before passenger service begins. That period is often one of the most demanding parts of the schedule because the project has to function as a fully coordinated transport system, not just as a completed civil structure. Section 1 also has to be understood within the timeline of the larger D-Line extension program. It is the first of 3 major sections, meaning its completion has operational importance beyond its own stations. Once open, it becomes the base from which the later western sections connect toward Beverly Hills, Century City, Westwood, and eventually the VA campus. That makes Section 1 the first visible delivery of a longer strategic investment that has been advancing in phases. By 2026, Brickell City Centre, Phase 2 is taking shape as a continuation of one of Miami's most influential mixed-use districts, with construction focused on adding new vertical density while expanding the pedestrian and retail ecosystem already established in Phase 1. In a city where projects must be delivered without shutting down surrounding streets, Phase 2 is built as a live integration job, tying new towers and public space upgrades into an operating urban complex. Construction activity in 2026 typically begins with the parts the public barely sees. Crews are deep into foundation and below-grade work, including drilled shafts, matte foundations, and waterproofed basement slabs designed for Miami's high water table. Utility reroutes and new service corridors are being installed early because Phase 2 has to expand electrical capacity, chilled water distribution, and telecom backbones without interrupting Phase 1 operations. Stormwater capture and pumping systems are also being upgraded to handle larger roof areas. New plazas and intensified runoff in heavy rain events Vertical construction in 2026 centers on the first major towers and podium structures. Concrete cores rise first to establish elevator shafts, stairwells, and riser pathways, followed by floor plate pours on a repetitive cycle. As soon as lower levels are enclosed, curtain wall installation begins to create weather-tight zones, allowing interior trades to move in while structural work continues above. This year's progress is measured by how quickly the project transitions from raw structure to concurrent fit-out. Because Brickell City Centre is known for high-performance public realm features, 2026 work also includes extensive streetscape and circulation construction. Pedestrian bridges, widened sidewalks, and redesigned drop-off zones are built in phases to maintain access to existing retail and transit connections. Traffic control modifications, signal timing upgrades, and loading dock routing are being implemented too. Manage delivery volumes and rideshare demand that increase as new components come online. Inside the new structures, mechanical and electrical installation is a major 2026 driver. Contractors are routing large duct mains, chilled water piping, fire protection systems, and emergency power pathways. Mixed-use buildings add complexity, so hotel, office, and residential zones, if included, require separate vertical risers, access control strategies, and dedicated back-of-house circulation. Data and security systems are embedded early, including fiber distribution, camera infrastructure, and building automation networks that will manage energy use across the expanded footprint. Retail and podium levels, where foot traffic concentrates, receive early attention in 2026. Structural framing and slab work are paired with rough-ins for grease exhaust, kitchen ventilation, and high-capacity electrical feeds that support food and beverage tenants. Public-facing finishes typically lag the structural schedule, but the groundwork for storefront glazing, escalators, and vertical circulation is installed now to avoid rework later. Timeline-wise, large mixed-use expansions like this are generally delivered as phased openings rather than a single completion date. In a 2026 construction context, Phase 2 is usually positioned for major structural milestones in the near term, followed by a multi-year sequence of enclosure, interior completion, tenant build-outs, and commissioning. The practical completion window is commonly late 2020s, with different components opening as they clear inspections and operational readiness. Away from the spotlight of game day, UNLV's football infrastructure work in Nevada in 2026 is centered on the facilities that determine week-to-week performance. Practice fields, player development spaces, and the technical backbone that supports modern college athletics. The stadium itself is only one piece of the system, and the 2026 construction focus is on improving the places where training, rehab, scouting, and operations happen every day. In 2026, a major share of the work is typically concentrated on the field environment. That means rebuilding practice surfaces with updated turf systems or improved natural grass profiles, adding better sub-drainage, and upgrading irrigation controls to handle extreme heat and water efficiency requirements. Field lighting upgrades are part of this package, with higher output LED arrays and improved aiming to support night training while reducing spill and energy use. Where fields are being regraded, crews also rebuild perimeter curbs, safety runoff zones, and fencing designed for controlled access and equipment movement. Inside the football operations and performance spaces, 2026 construction is about capacity and workflow. Strength and conditioning areas are expanded with higher floor load design for heavy equipment, improved ventilation for high occupancy training periods, and acoustical treatment to reduce echo in large rooms. Athletic training and sports medicine build-outs add dedicated hydrotherapy, physical therapy bays, and recovery zones, all requiring specialized plumbing, floor waterproofing, and electrical distribution for medical equipment. Player spaces are another focus in 2026, especially locker room and meeting room modernization. Renovations typically include larger locker footprints, improved showers and laundry routing, and better circulation so the building handles peak team movement before and after practices. Team meeting rooms and position rooms are upgraded with integrated AV, coach-to-player video systems, and data connectivity that supports film review and analytics. That drives a major 2026 scope item that doesn't read as dramatic on camera, but matters in construction. Structured cabling, server closets, Wi-Fi densification, and power conditioning for always-on broadcast and video gear. Stadium-adjacent upgrades in 2026 often involve operational efficiency and athlete logistics rather than visible architecture. This includes improved equipment storage, loading access for trucks and carts, secure entry points, and revised pedestrian paths that separate athlete movement from public circulation. If premium or fan-facing areas are part of the scope, 2026 work may also include targeted concourse improvements, upgraded concessions, back-of-house systems, and point-of-sale network expansion, all tied to electrical and data upgrades. The San Joaquin Valley is one of the most active frontiers for large-scale renewable energy deployment in the United States. Central to this transformation is the Westlands Solar Park, a vast solar generation complex occupying former agricultural land in western Fresno and Kings counties. At full build-out, the project is planned to exceed 2,700 megawatts of solar photovoltaic generation capacity, with enough output to power over 1.2 million homes annually. Construction activity at Westlands is ongoing in multiple phases in 2026. Several hundred megawatts of new capacity are being installed this year alone, involving tracker-mounted solar panels, inverter stations, and substation upgrades across various parcels of the site. The terrain consists of retired farmland, much of it previously deemed unusable due to salt buildup and water supply restrictions. These parcels are being repurposed for renewable energy under a land use framework coordinated with the Westlands Water District and state energy planners. New transmission infrastructure is also under construction in 2026 to connect additional generating blocks to the California Independent System Operator grid. This includes expansion of the Gate substation and integration of newly completed collector substations. Interconnection capacity is being increased to accommodate not only current solar projects, but also future energy storage systems that are now part of long-range build-out plans. In parallel with solar generation, battery energy storage is entering the construction pipeline. In 2026, multiple developers are installing utility-scale battery systems adjacent to solar arrays designed to store surplus daytime generation and discharge it during peak evening demand. These lithium-ion systems are being integrated directly with grid controls, supporting load balancing and reducing reliance on natural gas peaker plants. The development at Westlands is part of a larger regional shift. In 2026, the Western San Joaquin Valley hosts more than a dozen large renewable energy projects in various stages of permitting, construction, or operation. This includes both standalone solar fields and hybrid facilities with co-located batteries. Projects are distributed across counties, including Fresno, Kings, Kern, and Tulare, taking advantage of high solar irradiance, flat terrain, and proximity to major transmission corridors, such as Path 15 and the California-Oregon intertie. Permitting processes in 2026 have been streamlined under the state's renewable energy acceleration mandates, particularly those tied to SB 100 and the state's goal of reaching 100% zero-carbon electricity by 2045. Projects in Westlands benefit from environmental pre-clearance under the Renewable Energy Transmission Initiative, which has designated this area as a high-priority renewable energy zone. As a result, timelines from permitting to groundbreaking have shortened significantly in recent years. Employment across these projects in 2026 supports hundreds of construction jobs in electrical, civil, and mechanical trades. Labor agreements ensure prevailing wages and workforce training, while local agencies coordinate with developers on road improvements and service access. Equipment staging, panel deliveries, and interconnection work are active throughout the region, with multiple utility contractors working simultaneously across different sites. North of Dallas, in one of the fastest growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area megaprojects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex megaproject efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the mega project is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
Set in the rolling terrain of Fannin County, Texas, the Leonhurst Dam is a key feature in the development of Lake Ralph Hall, a major water supply reservoir under construction to meet the growing demands of the North Texas region. This dam is a crucial component of a broader infrastructure program designed to provide long-term water reliability while incorporating environmental and recreational benefits. The project includes an earthen embankment dam, intake and outlet structures, spillways, and various support facilities. By 2026, the dam embankment, outlet works, and much of the lake basin clearing and impoundment control systems are scheduled for completion, representing the functional establishment of the reservoir. The dam itself is a zoned earthfill embankment, meaning it is constructed using distinct layers of different soil materials, each selected for specific geotechnical properties. The central core is composed of low permeability clay, forming an impermeable barrier to prevent seepage. This core is flanked by progressively more permeable materials, sand, gravel, and rock, that provide both structural support and controlled drainage. These zones are compacted in thin lifts using heavy compaction equipment to achieve the necessary density and bonding between layers. Foundation preparation was one of the earliest and most critical steps in the construction process. It began with stripping of topsoil and removal of organic materials, followed by proof rolling and excavation down to suitable bearing strata. A cut-off trench was excavated beneath the core zone and keyed into bedrock or highly consolidated clay, effectively reducing the risk of underseepage. As an added precaution, grout curtains were drilled along the alignment to seal fractures and enhance subsurface impermeability. As the embankment rose, real-time monitoring was implemented using inclinometers, piezometers, and settlement gauges. These instruments provided engineers with continuous data on pore water pressures, lateral movement, and vertical deformation, allowing timely adjustments to fill placement and moisture conditioning. The upstream slope of the dam was armored with riprap to guard against wave action and erosion once the reservoir reaches operational levels, while the downstream slope was protected with turf reinforcement and slope drains. The outlet work structure, also on track for completion by 2026, consists of a reinforced concrete intake tower, gated conduit, and stilling basin. The intake tower includes multiple inlets at different elevations, allowing selective withdrawal for optimal water quality. Flow from the intake travels through a concrete-lined tunnel beneath the dam, controlled by a series of hydraulically operated gates and valves. At the toe of the dam, flow is discharged into a stilling basin lined with energy dissipation blocks and reinforced slabs to prevent scour and erosion. Spillway construction includes a broad-crested weir and a concrete chute extending down the abutment. The spillway is designed to safely pass the probable maximum flood without overtopping the embankment. It incorporates erosion-resistant lining and aerators to minimize cavitation effects during high-velocity flow events. By 2026, the dam embankment and hydraulic structures will be fully constructed, enabling the initial stages of reservoir impoundment and system commissioning. This milestone signifies the transformation of the site from an active construction zone into a functioning regional water resource, marking a major advancement in North Texas water infrastructure. The Chesapeake Bay Bridge Safety Enhancements Project in Maryland is about reinventing safety on one of the most critical and nerve-wracking crossings in the East Coast. Stretching 4.3 miles across the Chesapeake Bay, the Bay Bridge connects Annapolis on the western shore with Kent Island on the eastern shore. It carries over 25 million vehicles a year, but for decades, drivers dreaded it. Strong crosswinds, aging guardrails, and minimal emergency access made every crossing a gamble. By 2026, that's going to change. This proposed $280 million safety enhancement project focuses on storm hardening, real-time traffic management, and structural modernization, all while keeping the bridge operational. At the heart of the upgrade was the installation of wind protection barriers along the full span. These aerodynamic deflectors, engineered to reduce wind shear by up to 40%, now shield vehicles from dangerous gusts, especially those in high-profile trucks and SUVs. These barriers were manufactured in modular segments and lifted into place by high-lift barge-mounted cranes, operating only during low-traffic night windows. Equally transformative was the surface overhaul. Crews applied a high-friction epoxy overlay, a specialized treatment using resin mixed with aggregate, to improve tire grip during wet and icy conditions. This reduced crash rates by nearly 30% in early post-completion studies. To execute the work with minimal closures, workers used self-propelled modular transporters to bring in materials and machinery, keeping active traffic lanes free. Another major safety upgrade was the addition of intelligent lane control systems. Using overhead gantries, color-coded LED lane signals, and real-time sensors, the system can instantly change traffic direction during peak hours or emergencies. This system is tied to a centralized traffic command center in Annapolis, which also manages surveillance cameras, incident detection algorithms, and automated alerts for wrong-way drivers. Below the bridge, engineers conducted a full underwater retrofit. Divers working in pressurized suits and submersible remotely operated vehicles applied cathodic protection systems to the submerged piers. This electrochemical process prevents corrosion from salt water, extending the life of structure by decades. Meanwhile, seismic dampers were installed at key joints, providing additional stability during tremors or vessel strikes. The Bay Bridge now operates with a digital twin, a virtual, real-time model of the structure updated through thousands of IoT sensors tracking stress, vibration, temperature, and traffic loads. This data feeds into predictive maintenance models, allowing engineers to prevent failures before they happen. Set within Exposition Park in Los Angeles, the Lucas Museum of Narrative Art is one of the most distinctive cultural construction projects advancing toward completion in the United States in 2026. The project is designed as a major museum dedicated to narrative art in multiple forms, including illustration, painting, photography, comics, cinema-related material, and digital media, with a building program that also includes galleries, theaters, educational space, archives, public landscape, and visitor facilities. Its significance in the 2026 construction cycle comes from the fact that it is not a standard institutional building. It combines complex architecture, specialized museum systems, and extensive site integration in one of Los Angeles' most important civic districts. The structure itself is central to the project's identity. Unlike a conventional rectangular museum, the building is defined by a sculptural form with a continuous exterior envelope and a highly controlled interior environment. That architectural approach creates additional complexity in both construction and completion. The work is not limited to erecting floor plates and closing a facade. It requires precise coordination between structural systems, exterior cladding, waterproofing, environmental controls, and the interior gallery conditions needed for long-term preservation of artworks and archival materials. By the time the project reaches its 2026 completion phase, the most important work is concentrated on final enclosure, systems commissioning, interior fit-out, and landscape integration. Exterior construction in that period includes completion of the outer skin, sealing of the building envelope, roof finishing, drainage resolution, and the final detailing, required to protect the structure and create stable internal environmental performance. Inside the museum, the key construction activities include gallery finishing, installation of climate control systems, lighting systems, fire protection, security infrastructure, vertical transportation, theatre and presentation spaces, back-of-house support areas, and the specialized mechanical and electrical systems required for museum operations. A museum of this type also depends on exact environmental calibration before it can function. Completion is not achieved when the building is visually finished. The project has to move through balancing and testing of temperature and humidity controls, life safety certification, access control integration, audio-visual commissioning, and the preparation of collection handling spaces. Exhibition areas require carefully controlled lighting and air management. Storage and archive areas need stricter performance standards than many ordinary public buildings. That makes the final year of construction particularly technical because the project is transitioning from architectural completion into operational readiness. North of downtown Miami's traditional core, Miami Worldcenter in 2026 functions as a multi-site construction zone rather than a single project, with separate towers, public streets, and retail blocks being delivered in overlapping packages. In the Miami Megaproject landscape, under construction in 2026, its defining feature is sequencing. Infrastructure and public realm upgrades must be completed while new vertical buildings rise on adjacent parcels, all tied into an active transit district. In 2026, civil and streetscape construction is a major component of the work. Crews are completing permanent roadways through the district, adding new intersections, curb lines, and pedestrian crossings that stitch the development into the existing street grid. Utility expansion is continuous this year, including new water and sewer runs, stormwater piping, and electrical duct banks sized for high-rise loads. Because the site sits in a dense urban area, much of this work is staged block by block, with temporary traffic shifts and night work used to maintain access to existing businesses and transit corridors. Vertical construction continues in 2026 across multiple towers and podium structures. Concrete cores rise first, followed by repetitive floor plate pours and post-tensioning cycles that allow multiple high-rise teams to work in parallel. Curtain wall installation is advancing on lower levels to create weather-tight zones for interior trades, which is essential in Miami's rain-heavy seasons. As soon as floors are enclosed, mechanical, electrical, and plumbing rough-ins accelerate, including fire protection systems, vertical risers, and building automation infrastructure. Retail and entertainment components are being built out in 2026 as a network, not as isolated storefronts. That means interior shells are being delivered with coordinated grease exhaust, kitchen ventilation, and high-capacity electrical service for food, beverage, and nightlife tenants. Loading and waste management routes are being finalized behind the scenes to keep service traffic separated from pedestrian promenades. Public lighting, security cameras, and wayfinding systems are being installed early because the district is expected to operate in phases, with some blocks active while others remain under construction. Parking and mobility integration is another visible 2026 construction task. Garage structures and podium parking levels are being completed alongside pedestrian links that connect to nearby transit, including Metro Rail and Brightline access points, rideshare staging zones, bus interfaces, and protected pedestrian routes are being built to manage event peaks without overwhelming surrounding streets. Because Miami Worldcenter is a long horizon development, its timeline is defined by phased completions rather than a single opening date. By 2026, earlier components are already operating, while new towers, hotel additions, and street-level blocks continue to come online in stages. The late 2000s are generally positioned as a period when multiple remaining parcels reach completion, with full district build-out extending further depending on market absorption and project sequencing. Instead of a single building, the Clark County Innovation District in Nevada is, in 2026, a layered construction effort where the first visible results are roads, utilities, and site platforms that make future research and advanced industry development possible. The district is being built to attract technology companies, applied research partners, and workforce training programs, and the construction sequence reflects that goal. Infrastructure first, vertical development second, tenant fit-out last. In 2026, the main construction activity is district enablement. Crews are grading large parcels to final elevations, building retaining structures where needed, and installing the underground network that lets multiple future buildings connect without repeated excavation. That includes water and sewer mains, stormwater detention and filtration systems, and high-capacity electrical duct banks designed for energy-intensive uses like labs, data-rich operations, and prototyping spaces. Fiber is treated as core infrastructure, so conduit corridors and handholds are being installed in 2026 alongside power and water, not after buildings go up. Roadway construction is another major 2026 focus. New internal streets, turn lanes, and signalized intersections are being built to handle commuter peaks, deliveries, and transit access. Sidewalks, multi-use paths, and streetscape lighting are being added early because the district is meant to function as a walkable campus rather than a set of isolated office pads. Traffic circulation is planned around separate service routes, so delivery vehicles and construction trucks can move without crossing the pedestrian spine. Vertical construction in 2026, where it is underway, tends to concentrate on the first anchor facilities. These are typically flexible shell buildings designed for rapid tenant adaptation with higher floor loads, generous ceiling heights, and expandable mechanical rooms. Contractors are pouring foundations, erecting structural steel, and enclosing building shells so interior work can proceed as soon as tenants finalize requirements. Mechanical and electrical rough-ins are a major schedule driver in these early buildings because innovation tenants often require redundant power, enhanced cooling, and segmented ventilation for clean work areas or small-scale lab environments. Public realm and support infrastructure are also active in 2026. That includes site security perimeters, access control points, and camera and communications backbones that can scale as the district grows. Landscaping and water-efficient planting are installed in phases, often tied to stormwater features such as bioswales and retention basins that also serve as the district's environmental compliance system. The Pacheco Pass segment falls within the broader Merced to San Jose section, which is in the advanced pre-construction phase. Full-scale construction is expected to begin in late 2026 or early 2027, following the completion of design, environmental permitting, and contractor procurement. In 2026, geotechnical investigations are being conducted at multiple points across the alignment, including test drilling to analyze subsurface conditions, fault mapping near the Calaveras and San Andreas fault zones, and seismic risk assessments required for final tunnel engineering. The tunnel alignment will require 2 main bores with an internal diameter of approximately 40 feet each, separated by cross passages every 1,000 to 1,500 feet to allow emergency access and pressure equalization. An intermediate access shaft is also planned in the vicinity of Casa de Fruta to provide tunnel boring machine launch capability and logistical support during construction. The geology of the Diablo Range presents significant challenges with faulted rock zones, variable water inflows, and compressible soils in valley transitions. Tunneling will be conducted using pressurized tunnel boring machines capable of navigating mixed face and high pressure conditions. The Pacheco Pass tunnels will pass under critical infrastructure, protected habitat areas, and seismic fault lines, requiring advanced lining systems and continuous monitoring. Designs include seismic isolation joints and drainage galleries to mitigate fault displacement risk and groundwater intrusion. Tunnel depth will range from 100 to over 1,000 feet below surface, depending on terrain. Ventilation and safety systems, including emergency egress, fire protection, and pressurization controls, are part of the ongoing systems design effort in 2026. Upon completion, the tunnels will enable a seamless high-speed rail corridor from Merced to Gilroy, reducing rail travel time across the pass from over an hour to just under 15 minutes. Combined with viaducts, embankments, and cut and fill sections across the San Joaquin Valley and into the Santa Clara Valley, the Pacheco Pass alignment represents one of the most capital-intensive and engineering-heavy components of the entire HSR system. The full Merced to San Jose segment is targeted for phased operational readiness beginning in the early 2030s, contingent on funding and right-of-way clearance. In 2026, contract packaging and procurement strategy are being finalized. The tunnel construction will likely be delivered as part of a design-build package, integrating civil structures, systems, and tunnel fit-out under a single delivery framework. Coordination with Caltrain and Union Pacific Railroad in the Gilroy area is also active in 2026, where blended operations with existing rail infrastructure are being planned. At full build-out, the Pacheco Pass tunnels will serve as the gateway between the Central Valley's agricultural and inland urban centers and the tech-driven economy of Northern California. The tunnels are expected to handle multiple high-speed rail trains per hour in each direction, forming a high-capacity backbone for statewide intercity travel. Their construction, once launched, will take an estimated 6 to 7 years, involving around-the-clock excavation and a continuous logistics chain to manage spoil removal, liner segment installation, and tunnel utility integration. At the center of North Texas's expanding regional rail network, the BART Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signalling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the BART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest-growing metropolitan regions in the United States.
Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing staged disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027.
Rising from the ground in Orchard Park, New York, the new Highmark Stadium is a major construction endeavor aimed at delivering a state-of-the-art home for the Buffalo Bills and redefining the game day experience in Western New York. This open-air stadium replaces the aging original Highmark Stadium and is being built with a focus on durability, fan engagement, and advanced operational systems suitable for the harsh winter climate of the region. By 2026, the structural steel framing, precast concrete bowl, and building envelope are all projected to be complete, marking a major milestone in the stadium's delivery timeline. Construction began with extensive site grading and earthwork to shape the subgrade and install foundational infrastructure. The site preparation phase involved removal of unsuitable soils, installation of stormwater management systems, and placement of engineered fill to ensure proper compaction and drainage. Deep foundations using drilled shafts and large diameter piers were installed to support the stadium's superstructure, particularly beneath the main seating bowl and roof canopy supports. These foundations were embedded into the region's bedrock using high-capacity rebar cages and tremie-poured concrete to deliver structural stability under heavy snow and wind loads. Once the foundation work was finalized, erection of the stadium's structural steel frame commenced. Large steel columns and trusses were fabricated off-site and transported in segments to be assembled using high-capacity crawler cranes and bolted field connections. The steel structure forms the skeletal framework for the seating tiers, premium suites, press boxes, and canopy roof system. Parallel to this, precast concrete risers and seating platforms were installed in a stepped sequence to form the lower and upper bowls. These concrete components are cast with integrated utility conduits and anchorage points for seats, railings, and electrical fixtures. A major feature of the stadium is its asymmetrical canopy design, which is intended to shield the majority of fans from snowfall and wind while leaving the playing field open to the elements in true Buffalo fashion. The canopy is supported by a series of tapered box girders and cantilevered trusses extending outward from the upper bowl's compression ring. Roof decking includes insulated metal panels with integrated snow guards and drainage paths to direct meltwater safely to ground level. Mechanical, electrical, and plumbing systems have been progressing simultaneously with structural work. Central utility corridors were embedded into the lower levels, carrying chilled water, gas, electrical service, and communication cabling. Utility nodes are distributed throughout the concourses and suites to accommodate concession equipment, digital signage, lighting, and ventilation. High-efficiency HVAC units, snowmelt systems for walkways, and smart lighting controls are all part of the sustainable design strategy. By 2026, the entire stadium structure, including the concrete bowl and canopy roof, will be completed and fully enclosed. This enables interior fit-out phases to begin, which will involve installation of seats, finishes, digital infrastructure, and audio-visual systems. The building envelope, consisting of curtain wall glazing, insulated metal panels, and high-performance weatherproofing, will be sealed to withstand Western New York's freeze-thaw cycles and high wind events. The Grand Parkway expansion in Houston, Texas, is one of the largest highway infrastructure undertakings in the southern United States. Officially designated as State Highway 99, the Grand Parkway is a massive loop encircling the Houston metropolitan area. With rapid population growth and heavy commercial traffic burdening existing routes like I-10 and Beltway 8, this expansion was a logistical necessity. The segments H, I-1, and I-2, completed by late 2025, added over 52 miles of new highway lanes connecting Harris, Montgomery, Chambers, and Liberty counties. The final cost of the project exceeded $1.28 billion, financed through a combination of state funds and toll revenue bonds. The construction focused on 6-lane divided highways with full-grade separated interchanges, frontage roads, and intelligent traffic systems. Each segment was designed for heavy-load commercial vehicles, with pavement engineered to handle decades of truck traffic without structural degradation. What sets this project apart was the deployment of advanced construction technologies. Engineers used LiDAR-based terrain scanning and drone-assisted surveying to map flood-prone areas and adjust elevations accordingly. This was critical, given the vulnerability of Houston to flooding during hurricanes and storm surges. Geotextile reinforced soil embankments were employed to stabilize the ground, especially in the marshy zones of eastern Harris County. In terms of machinery, the expansion utilized automated paving machines, soil compaction drones, and mobile concrete batching units, which enabled high-speed on-site mixing. To speed up bridge construction over waterways and railroads, teams deployed segmental bridge launching gantries. This allows entire spans to be placed without disrupting existing traffic or requiring extensive scaffolding. One of the biggest challenges was working around existing neighborhoods and ecosystems. The project included over 40 new wildlife crossings, sound barrier walls, and stormwater detention ponds to minimize environmental impact. The lanes were equipped with intelligent transportation system technology. Embedded sensors and cameras feed live data to control centers, enabling dynamic toll pricing, real-time traffic redirection, and emergency vehicle preemption systems. For commuters, the impact is already visible. A drive that once took 90 minutes during rush hour can now be completed in less than 45 minutes. Suburban areas like Cypress, New Caney, and Baytown are seeing a boom in residential development, thanks to improved access. For the trucking industry, the loop has shaved off millions in annual fuel and delay costs. The Grand Parkway expansion is a masterclass in how Texas handles growth with speed, scale, and strategic vision. It moves economies, linking major ports, warehouses, and business parks into a single high-speed corridor. Off the coast of Virginia, the Coastal Virginia Offshore Wind Project is scheduled to reach its defining construction phase in 2026, when the offshore installation campaign and grid connection work are expected to push the development from a marine works program into an operating energy asset. This is one of the largest energy megaprojects advancing toward completion in the United States, built to establish a commercial-scale offshore wind facility in federal waters east of Virginia Beach and to deliver a major new source of electricity into the regional grid. The project consists of a large field of offshore wind turbines, subsea cable systems, offshore substations, onshore transmission connections, and the related port and logistics infrastructure needed to assemble, transport, and install heavy components at sea. Its scale makes it different from earlier US offshore wind efforts. This is not a pilot installation or a small demonstration array. It is a utility-scale generation project intended to add substantial capacity through a coordinated marine construction effort involving specialized vessels, fabrication supply chains, and grid integration works on land. The most important construction activity associated with completion in 2026 is the offshore erection sequence. By that stage, work is focused on installing turbine foundations, transition pieces, towers, nacelles, and blades, along with completing offshore substations and laying or finishing inter-array and export cables. Each of these activities depends on weather windows, vessel availability, marine coordination, and strict sequencing. Foundation and cable work must be sufficiently advanced before final turbine installation can move efficiently, and energization cannot occur until both offshore and onshore systems are ready for integrated testing. Onshore construction in 2026 is also essential to completion. That includes cable landfall works, underground or corridor-based transmission connections, substation completion, electrical equipment installation, control systems integration, and final commissioning preparations. For a project of this kind, completion is not defined only by the last turbine standing offshore. It depends on the point when generation equipment, transmission, infrastructure, protection systems, and grid connection assets are all tested together and accepted for service. By 2026, the Brightline Miami to Orlando corridor is less about building a brand new railway and more about expanding the capacity and reliability of an intercity system that now has to perform like daily infrastructure. In the Miami megaproject context, the construction story in 2026 is a mix of corridor hardening, speed and schedule improvements, and station area build-outs that let the service handle higher ridership without degrading on-time performance. A major 2026 workstream is right-of-way and track capacity. Crews focus on additional double tracking in remaining single-track segments, plus new crossovers and turnouts that allow trains to pass and recover from delays. That work includes ballast and subgrade, improvements, replacement of rail fasteners and ties in high-wear zones, and drainage upgrades where South Florida rain events can saturate track beds and reduce stability. Bridge approaches and elevated sections receive structural inspections and targeted reinforcement so the line can maintain consistent speeds without imposing seasonal slow orders. Grade crossings remain a defining constraint for any Florida passenger line that runs at higher speeds. In 2026, construction activity typically concentrates on upgrading crossing surfaces, installing improved warning systems, and adding intrusion detection where feasible. Roadway tie-ins and traffic signal coordination near crossings are part of the same package, because the goal is not only safety, but fewer unplanned slowdowns caused by vehicle conflicts and queue spillback. Systems work expands in parallel. In 2026, signal and communications upgrades are key, including new equipment huts, fiber runs, and power conditioning systems that stabilize train control and dispatching. Where higher frequencies are planned, the corridor needs tighter block spacing and more resilient redundancy, so crews are installing and testing additional wayside hardware and networked monitoring equipment that feeds centralized operations. Stations and terminal interfaces also drive construction in 2026, especially around Miami Central and the Orlando Airport Terminal, where passenger volumes create pressure on circulation space. Work in this phase tends to include platform and canopy improvements, expanded vertical circulation, and upgraded passenger processing areas such as queuing, ticketing, and security-adjacent zones. Back-of-house systems are upgraded too, including maintenance access, cleaning and servicing areas, and power distribution that supports more frequent departures. A less visible but critical 2026 construction program is resilience. Coastal South Florida infrastructure has to account for flooding, salt corrosion, and extreme heat. That pushes investment into corrosion protection, electrical room hardening, improved pumping, and drainage at low points, and redundant communications pathways so service can be restored quickly after severe weather. In the Las Vegas Valley, the Intermountain Health Children's Hospital project is one of Nevada's most consequential healthcare builds, still under construction in 2026. The facility is being delivered as a dedicated pediatric hospital designed to expand specialty care capacity, reduce the need for families to travel out of state, and create a modern hub for children's emergency, inpatient, and surgical services. By 2026, the project is in its intensive build-out phase. The structural frame and building enclosure are advancing, and the construction focus has shifted toward the systems that make a hospital function safely. Mechanical, electrical, and plumbing trades are installing the backbone infrastructure floor by floor: large air handling units, medical gas lines, fire protection piping, and redundant electrical distribution. Critical care spaces require strict air pressure relationships and infection control measures, so 2026 work includes commissioning of HVAC zones, sealing of penetrations, and installation of filtration systems sized for operating rooms, isolation rooms, and neonatal care environments. Interior construction in 2026 is also defined by specialized build requirements. Patient rooms are framed and roughed in with head walls that integrate oxygen, vacuum, data, and nurse call systems. Imaging areas require structural support and shielding coordination, so contractors are placing lead-lined assemblies, vibration mitigation, and dedicated power feeds for MRI, CT, and interventional equipment. Surgical suites and procedure rooms move through a tightly sequenced workflow in 2026. Wall framing, above-ceiling service booms, low-voltage integration, and cleanable finish packages designed for infection prevention. Outside the building, site infrastructure remains active in 2026. Work includes final grading, stormwater management, and the construction of ambulance and service access routes that separate emergency circulation from public drop-offs. Utility tie-ins are a major task this year, especially for redundant power and backup generation. Hospitals require continuous operation, so 2026 construction includes generator yard installation, fuel systems, automatic transfer switches, and testing protocols that verify the facility can sustain critical loads during grid outages. Technology integration is another defining 2026 scope item. Data closets, fiber runs, and wireless infrastructure are being installed early because clinical systems depend on reliable connectivity. Security and access control systems are layered in as areas are enclosed, including camera networks, controlled staff entries, and infant security features typical of pediatric facilities. In 2026, construction begins in earnest on the Los Angeles Metro Southeast Gateway Line, a major light rail expansion aimed at delivering high-capacity transit service to some of the most densely populated and historically underserved communities in southeast Los Angeles County. Previously known as the West Santa Ana Branch Transit Corridor, this project represents one of the largest new rail corridors in the region and forms a critical part of the county's long-term Measure M mobility strategy. The project's first operational phase will span 14.5 miles, linking the existing A-Line station at Slauson in South Los Angeles to a new terminal station at Pioneer Boulevard in Artesia. This segment will include 9 new stations and is designed to serve communities across Huntington Park, Bell, Cudahy, Southgate, Downey, Paramount, Bellflower, and Artesia. As of 2026, the corridor is in the early stages of pre-construction and enabling works, with heavy utility, relocation, environmental mitigation, and corridor preparation now underway. Utility relocation is a primary focus in 2026. In multiple cities along the alignment, electrical, gas, water, and telecommunications lines are being moved to accommodate future construction of the light rail guideway and associated infrastructure. In Artesia, crews are also performing grading work and beginning access improvements in preparation for major station excavation and track installation, which is expected to ramp up in 2027. The project is being delivered under a progressive design-build model. A joint venture of Flatiron, Dragados USA, and Herzog is leading the initial pre-construction phase under a contract valued at over $997 million. This early work includes soil testing, demolition of outdated facilities, geotechnical surveys, and engineering refinements along the right-of-way. These preparatory efforts are critical to mitigating delays once full construction begins. The total cost? For the Southeast Gateway Line, Phase 1 is projected at approximately $8.6 billion. The project is being funded through a combination of local sales tax measures, including measures R and M, along with state transportation funds and a significant request for federal support through the FTA's New Starts Capital Investment Program. Metro is targeting a full funding grant agreement from the federal government by 2027. The alignment follows a former Pacific Electric Railway corridor with portions of the route adjacent to active freight lines. In 2026, Metro and its construction partners are actively coordinating with freight rail operators to ensure clearances, right-of-way agreements, and safety systems are in place. Quiet zones, grade separation structures, and fencing are being designed, and in some areas, early site work has begun. The line will use low-floor light rail vehicles, similar to those operating on Metro's existing lines, with stations designed for full ADA accessibility. Platforms, traction power substations, and signal control infrastructure are all in the design phase in 2026, with final engineering packages expected to be released for construction bidding in 2027. Far south of Dallas, in Ellis County, near the city of Midlothian, the Google Data Center campus stands as one of the most infrastructure-intensive megaprojects under construction in the North Texas region in 2026. Unlike high-visibility urban developments, this project is defined by scale, power demand, and systems complexity, with construction activity focused on creating long-term digital infrastructure rather than public-facing architecture. The Midlothian Data Center is part of Google's broader expansion of hyperscale computing capacity in Texas, selected for its access to land, transmission infrastructure, and regional redundancy. The site is planned as a multi-building campus rather than a single structure, allowing phased expansion over several years. This phased approach makes 2026 a key construction year, as initial facilities transition from shell construction to systems-heavy build-out. By 2026, site-wide civil and utility infrastructure is largely established, enabling vertical construction and interior fit-out to dominate activity. Primary data hall buildings are either topped out or approaching structural completion, with reinforced concrete frames and steel roof systems designed to support heavy mechanical loads. These structures prioritize clear spans, high floor loading capacity, and modular expansion potential. Mechanical and electrical construction is the defining feature of 2026 work. Crews are installing large-scale power distribution systems, including substations, switchgear yards, and redundant electrical pathways. Multiple layers of redundancy are built into the campus, requiring parallel systems for primary and backup power. This includes integration with regional transmission lines and on-site backup generation infrastructure. Cooling infrastructure is another major focus during 2026. Data center cooling plants, including cooling towers, chillers, and water treatment systems, are under active construction. These systems are designed to handle continuous high-density server loads while optimizing water and energy efficiency. Piping networks connecting cooling plants to individual data halls are installed underground and within service corridors throughout the campus. Interior build-out of data halls accelerates in 2026. Raised floor systems or slab-integrated airflow designs are installed depending on building configuration. Server rack infrastructure, cable trays, and fire suppression systems are constructed in tightly sequenced phases. Fire protection systems typically use specialized suppression methods designed for sensitive electronic environments, requiring extensive testing and commissioning. Support buildings and ancillary facilities are also under construction in 2026. These include network operations centers, security facilities, maintenance buildings, and office space for on-site technical staff. These structures are less visually dominant, but critical for day-to-day operation and monitoring of the data center campus. Security and perimeter infrastructure advances significantly during 2026. The site includes layered physical security systems such as perimeter fencing, controlled access points, surveillance infrastructure, and secure internal zoning. Much of this construction is integrated into site grading and landscaping to maintain operational separation without excessive visual impact. Water and environmental infrastructure remains active throughout 2026. New water supply connections, storage tanks, and wastewater systems are completed or expanded to support cooling operations. Stormwater management features, including retention ponds and drainage systems, are finalized to meet regulatory requirements and protect surrounding land from runoff impacts. From a timeline perspective, 2026 represents a transition from heavy shell construction to commissioning-focused activity. While new buildings may still be under construction, several completed structures enter systems testing phases. Electrical load testing, cooling system commissioning, and network validation are conducted incrementally as each facility segment reaches readiness. Construction activity is expected to continue beyond 2026, with additional data halls and support facilities added in subsequent phases. Full campus build-out is typically planned over multiple years, allowing capacity to scale with demand. Initial operational capability is often achieved before total completion, with sections of the campus coming online independently.
In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central Soma. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, the rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central Soma for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, while major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the rail yard site not just a place to live and work, but a critical node in the future of statewide transit.
Amid the complex subterranean infrastructure of New York City, the 2nd Avenue Subway Phase 2 project represents a major expansion of transit capacity along Manhattan's East Side, particularly servicing the underserved East Harlem neighborhood. This phase extends the Q line northward from the current terminus at 96th Street up to 125th Street, adding approximately 1.5 miles of new twin-track tunnel and 3 new stations at 106th Street, 116th Street, and 125th Street. Although full completion is expected later, significant early works, tunneling activities, and utility relocations are on schedule to be finalized by 2026, marking a critical milestone in the overall construction timeline. Initial construction efforts have focused on the relocation and protection of underground utilities, a process that requires precision excavation through layers of densely packed infrastructure, including sewer lines, water mains, gas conduits, electrical cables, and telecommunication systems. To accomplish this safely, crews utilized vacuum excavation methods and non-destructive digging tools, mapping utility alignments and rerouting them to clear paths for future excavation. In some areas, new utility corridors were built entirely to support the tunnel boring operations and future station development. Once the utility work reached sufficient progress, tunneling operations commenced with the deployment of tunnel boring machines that were lowered into deep launch boxes constructed along the alignment. These TBMs are massive cylindrical machines equipped with rotating cutter heads designed to bore through Manhattan schist and other geologic layers. As they advanced, the machines simultaneously installed precast concrete tunnel lining segments, forming the structural shell of the subway tunnels. The twin tubes are built with precise curvature and grade to meet performance standards for modern train speeds and passenger comfort. In parallel with tunneling, deep excavation began for the future station caverns. Each station box, particularly the 125th Street Terminal, is being constructed using a combination of cut-and-cover methods and sequential excavation techniques where appropriate. For deeper sections, rock blasting and mechanical excavation were employed under controlled conditions, with vibration monitoring in place to protect surrounding buildings and infrastructure. Excavated material is removed using muck conveyors and trucked out via dedicated access shafts. One of the most significant aspects scheduled for substantial completion by 2026 is the structural excavation and primary concrete shell of the 125th Street Station. This includes the reinforced concrete station box, invert slab, and column and beam framework that will support platform levels, mezzanines, and ancillary rooms. The work also encompasses critical elements of vertical circulation infrastructure such as elevator and escalator shafts. Completion of this shell by 2026 will allow fit-out phases such as mechanical, electrical, and plumbing installation to begin immediately thereafter. Throughout the alignment, permanent structural support systems like slurry walls, rock bolts, shotcrete linings, and waterproofing membranes are being installed in stages, often following close behind excavation fronts. Utility infrastructure is being rebuilt to modern standards with upgraded capacity, redundant power feeds, and new stormwater management systems. By 2026, the completion of tunneling, station cavern excavation, and core structural concrete work marks a pivotal transition point in Phase 2 of the 2nd Avenue subway. It sets the stage for the interior outfitting, systems installation, and track work that will follow, ultimately advancing the long-awaited goal of extending high-capacity subway access to communities that have endured generations without it. Let's move over to the Empire Wind, one project, a transformative offshore wind initiative poised to reshape the energy landscape of New York. Empire Wind 1 is a cornerstone in the ambitious plan of New York to achieve 9,000 megawatts of offshore wind energy by 2035. With a capacity of 810 megawatts, this project is designed to supply clean electricity to approximately 500,000 homes in New York City, significantly reducing greenhouse gas emissions and advancing the climate goals of the state. Located about 15 to 30 miles southeast of Long Island, Empire Wind 1 encompasses an area of 80,000 acres. The project will consist of 54 Vestas, 15 megawatt wind turbines, each standing over 850 feet tall, making them some of the largest and most powerful turbines in operation. These turbines will be connected via subsea cables to an onshore substation at the South Brooklyn Marine Terminal in Sunset Park, Brooklyn. From there, electricity will be transmitted to the Gowanus substation, integrating seamlessly into the power grid of New York City. The estimated investment for Empire Wind 1 is around $2.5 billion. Beyond providing renewable energy, the project is expected to generate significant economic benefits, including the creation of over 1,000 union jobs during the construction phase and approximately 300 long-term jobs for operations and maintenance. The redevelopment of South Brooklyn Marine Terminal into a state-of-the-art offshore windport facility is also anticipated to stimulate local economic activity and establish a robust supply chain for future offshore wind projects. The construction of Empire Wind 1 involves advanced engineering and specialized equipment, including heavy lift vessels used for transporting and installing massive turbine components at sea. Jack-up rigs provide stable platforms for turbine installation in deep waters. Horizontal directional drilling employed for laying subsea cables with minimal environmental impact, while aircraft detection lighting systems are integrated into turbines to minimize light pollution by activating lights only when aircraft are detected. Currently, the Empire Wind one has achieved several critical milestones. The Bureau of Ocean Energy Management approved the construction and operations plan in February 2024, allowing construction to proceed. However, in April 2025, the U.S. Department of the Interior issued a halt to construction, citing the need for further environmental review. Linking hydropower from Canada directly into New York, the Champlain Hudson Power Express is one of the most consequential transmission megaprojects moving toward completion in the United States in 2026. The project is a long-distance, high-voltage direct current line designed to carry electricity from Quebec into New York City through a predominantly buried and underwater route. Its importance comes from both function and route strategy. Instead of relying mainly on new overhead corridors, the line is built largely beneath Lake Champlain, the Hudson River, and selected land segments, reducing surface disruption while creating a major new clean power connection into one of the country's largest electricity markets. The project consists of transmission cables, converter station infrastructure, landfall construction, buried terrestrial segments, underwater, installation works, interconnection facilities, and the control systems needed to operate an HVDC link across a long and technically varied corridor. Unlike a conventional generation project, this is an energy delivery mega project. Its value depends on whether the line can be physically installed, electrically integrated, and commissioned as a complete corridor. That makes the final construction period in 2026 especially important, because the system only becomes useful when the entire route and terminal equipment are ready together. The key construction work associated with 2026 completion is concentrated on the final cable installation segments, jointing and burial work, shoreline and transition point completion, and the finishing and energization of converter facilities. For a project using long submarine and underground cable runs, completion is not simply a matter of laying cable. Crews also have to complete trenching where required, backfill and protection measures, splice, vault work, cable testing, restoration of disturbed land segments, and the final interface between marine installed and land-based sections. Converter station work is equally critical, including installation of power electronics, transformers, cooling systems, protection equipment, control systems, and grid interconnection infrastructure. The schedule significance of 2026 is tied to the project's shift from corridor construction to electrical readiness. Earlier phases are dominated by permitting, manufacturing, route preparation, marine logistics, and initial installation campaigns. By the final approach to service, the project enters a more technical stage defined by testing and commissioning. High voltage direct current transmission requires extensive verification before operation. Insulation integrity, converter performance, communications, protection schemes, and system synchronization all have to be proven before the line can enter commercial service. That means the decisive work in 2026 includes not only physical construction, but also the final electrical and operational validation of the entire connection. Just west of downtown Miami, the Miami Freedom Park development is, in 2026, a multi-component construction site where a new soccer stadium is being built alongside a larger mixed-use district. It's positioned as one of the region's most visible mega projects because the schedule has to balance stadium delivery, public realm work, and the infrastructure needed to support daily operations and event surges. In 2026, the construction effort is typically split between 3 parallel tracks: the stadium structure, site-wide civil infrastructure, and the first wave of surrounding commercial buildings. On the stadium side, the core work is the seating bowl and the long-span roof system. Crews focus on concrete pours for raker beams, concourse slabs, and vertical circulation cores, while structural steel erection advances for roof trusses, canopy framing, and catwalk supports. As the building enclosure tightens, contractors shift into mechanical and electrical rough-ins, including air distribution, smoke control, emergency power pathways, and the backbone cabling for broadcast, security, and ticketing. Site infrastructure is a dominant 2026 scope item because the project sits on a large former industrial footprint that requires major utility reconstruction. Civil crews are installing stormwater detention and filtration features sized for intense South Florida. Rainfall, water, sewer, and fire service mains are being routed to support both the stadium and future district parcels. Roadway geometry is being rebuilt with signalized access points, internal service roads, and designated zones for rideshare, buses, and deliveries, all designed to keep event traffic from collapsing surrounding arterials. Another major 2026 activity is the public realm build-out. Pedestrian corridors, plazas, and landscaped buffers are being graded and poured early because they also function as construction circulation routes and staging areas. Lighting foundations, conduit banks, and security camera infrastructure are typically embedded before final paving so the district can open with functioning wayfinding and safety systems. Inside the stadium footprint, in 2026, fit-out work begins wherever sections are enclosed. That includes framing for locker rooms, media spaces, operations offices, concessions back of house, and premium hospitality areas. Kitchen, ventilation, grease waste systems, and high-capacity electrical feeds are installed early to avoid rework. Audio systems, ribbon boards, and scoreboard support steel are coordinated during this phase because they affect structural loading and access. Timeline-wise, projects like Miami Freedom Park are usually delivered in phases rather than as a single, all-at-once opening. The stadium is typically prioritized first, with surrounding retail, offices, and hospitality elements following in later packages as leases, financing, and tenant requirements are finalized. If full construction is active through 2026, a common delivery pattern is stadium completion in the near term after the main structure and roof are closed in, followed by months of commissioning, life safety testing, and operational readiness, while the wider district continues building into subsequent years. Out in Nevada's open desert and mountain basins, the Greenlink West project is, in 2026, a construction effort measured in miles of right-of-way and thousands of pieces of steel hardware rather than a single landmark. NV Energy's Greenlink West is a new high-voltage transmission corridor intended to strengthen the state's north-south power backbone, move renewable generation to where demand is growing, and reduce congestion on older transmission paths. In 2026, the work on Greenlink West is dominated by corridor build-out. Surveying and staking crews are finalizing tower locations and access routes, while civil teams are cutting and improving service roads to reach remote structure sites year-round. Foundation work is continuous through the construction season, with drill rigs and concrete pours forming the bases for lattice towers and monopoles depending on terrain and design. In rocky areas, crews are doing blasting, anchoring, and specialized grouting to achieve the required uplift and lateral resistance for tall transmission structures exposed to wind and temperature swings. Structure assembly is a visible 2026 milestone. Steel sections arrive by truck, are staged in laydown yards, and are lifted into place by cranes where access allows. In tighter terrain, crews use smaller cranes and multi-step picks, assembling sections on the ground and walking them upright. At the same time, grounding systems are being installed at each structure to manage lightning and fault currents, with bonding and earthing designed to protect both the line and nearby infrastructure. Conductor installation ramps up as contiguous stretches of towers are completed. In 2026, this means stringing pilot lines, pulling conductors through travelers, tensioning to spec, and clipping in hardware that controls vibration and galloping in high winds. Fiber optic communications lines are typically installed alongside the conductors, so the grid operator can monitor line conditions, control substations, and support protective relaying with low latency links. Substation and interconnection work is a parallel track in 2026. New or expanded substations require heavy foundations, steel gantries, breakers, transformers, and control houses. Electrical crews are building buswork, installing protection and control panels, and commissioning SCADA connections. These nodes are where Greenlink West becomes useful, because they determine how power is routed between regions and how new solar, geothermal, and storage projects can connect reliably. Environmental and permitting commitments stay active during construction. In 2026, that includes erosion control, dust management, wildlife timing windows, and restoration work behind the moving construction front, especially where access roads cross washes or sensitive habitat. One of the most complex airport infrastructure undertakings in the United States is nearing critical completion at Los Angeles International Airport in 2026. The Landside Access Modernization Program, or LAMP, is a $5.5 billion capital investment project reshaping ground transportation access to LAX. Its core components are designed to eliminate decades of congestion by reconfiguring how passengers arrive at and depart from one of the busiest airports in the world. At the center of the program is the 2.25-mile automated people mover, an elevated train system that will connect terminals to new off-site facilities. By 2026, all 6 stations of the APM are in advanced phases of construction. Guideway installation is complete, and systems integration is actively underway. This includes communications, train control, traction power, and platform screen doors. Testing of the first train sets began in 2024, and full pre-revenue operations are scheduled for mid-2026, with the line expected to open to the public later in the year. The APM will operate 24 hours a day, with peak headways of under 3 minutes, linking the central terminal area with 3 major intermodal access points: the Consolidated Rent-A-Car Facility, the Intermodal Transportation Facility, West, and the future Airport Metro Connector Station at 96th Street. These access points are critical to shifting passenger movement away from curbside traffic. Construction of the Conrack facility is substantially complete in 2026. Located east of the 405 freeway, this 5.3 million square foot structure consolidates over 20 rental car operations into a single vertical facility, reducing shuttle trips by over 3,000 daily. The facility includes ready return areas, maintenance bays, fueling stations, and direct access to the APM. Operational turnover to rental car companies began in late 2025, with phased occupancy continuing through 2026. The ITF West, a major drop-off and pickup location with public parking, opened in 2021, but continues to evolve in 2026 with integration of pedestrian pathways, wayfinding systems, and last-mile transit connections. The facility includes nearly 4,300 parking spaces and serves as the western terminus of the APM. It also supports the broader mobility plan by acting as a ground transportation hub with connections to shuttles, rideshare services, and regional buses. On the eastern side of the system, construction of the Airport Metro Connector Station, led by LA Metro, is active in 2026. This facility will link the APM to the regional rail network via the Metro K line and future expansions. Platform structure, track installation, and system integration are progressing, with projected completion targeted for 2027. When operational, it will allow passengers to reach LAX from the Metro system without the need for a vehicle. Additional work in 2026 includes extensive roadway realignment within the central terminal area. This involves upgrading access roads, curbs, and signage to match the new passenger circulation model, including drop-off lanes designed for rapid movement to the APM platforms. Pedestrian bridges linking terminals to the APM stations are in final construction stages, involving glass installation, elevator commissioning, and ADA compliance checks. The LAMP project also integrates sustainability features. Solar panels, electric, vehicle infrastructure, and stormwater capture systems are being commissioned across multiple facilities. The APM itself is all electric, designed to reduce greenhouse gas emissions by over 30,000 metric tons annually once fully operational.
In 2026, right in the heart of San Francisco's Soma district, the 5M project stands as one of the city's most active megaprojects under construction. This mixed-use development is bringing new energy and density to the blocks surrounding Mission, 5th, and Howard Streets. Long a patchwork of surface lots and low-rise structures, designed to create a live work-play ecosystem in the center of downtown. The 5M project is pushing forward this year with the final phases of its build-out, aiming for full completion by 2027. The core of the project is a multi-building, multi-acre redevelopment that includes housing, office space, community facilities, and public plazas. As of 2026, the residential component is nearing its final stages, with interiors being completed, amenity spaces outfitted, and streetscape work wrapping up. One of the tallest residential towers in the project, now visibly finished on the exterior, is expected to open its doors by early 2027, offering a mix of market-rate and affordable units, over 300 in total. The office and commercial buildings that anchor the project are also active hubs of construction. Fit-outs are progressing in multiple towers, preparing space for tech, nonprofit, and creative sector tenants. In 2026, these buildings are expected to start welcoming their first occupants by the end of the year, with full occupancy likely achieved in 2027. It's part of a broader shift in the area, as Soma continues to re-establish itself not just as a tech district, but as a vibrant, mixed-use downtown core. What sets 5M apart in the landscape of San Francisco's 2026 megaprojects is its emphasis on integration with the community. More than just a real estate development, the project was designed to create active public space and cultural infrastructure. At the center of the site, the 5M Park, currently under construction, is being landscaped with flexible gathering areas, art installations, and play zones for families. This green space is scheduled to open alongside the residential buildings in mid-2027 and is expected to become a crucial urban amenity for residents, workers, and visitors alike. This year, the construction crews are focused not only on completing vertical structures, but also on activating the ground plane. Sidewalks are being widened, bike infrastructure is going in, and retail storefronts are being prepped for future cafes, shops, and local businesses. The aim in 2026 is to finish creating a neighborhood that doesn't shut down after office hours, a place where people live, work, eat, and gather 7 days a week. One of the most significant elements under construction now is the dedicated nonprofit office hub and art space, which will house multiple local organizations and creative initiatives. This facility is central to the 5M vision, supporting equity, inclusion, and community-based growth in a rapidly evolving part of the city. Completion is on track for late 2026, with programming expected to launch shortly after. From a development standpoint, the 5M project is compact compared to some of the sprawling waterfront megaprojects elsewhere in San Francisco. But in 2026, it punches far above its weight in terms of impact. Located just blocks from Powell Street BART and Muni lines, its density and transit connectivity make it a model of sustainable urban development, and its blend of housing, employment, and civic use is already influencing how other central city projects are being designed.
Towering cranes and steel skeletons have come to define the skyline around Nashville International Airport, where the BNA Vision project is unfolding as a multi-phase transformation of terminal infrastructure, passenger amenities, and operational capacity. This sweeping development plan is designed to accommodate explosive regional growth and rising air travel demand. As part of this ongoing program, by 2026, Several major components will reach full completion, including expanded concourses, a new on-airport hotel, and integrated ground transportation facilities, all aimed at redefining the traveller experience while future-proofing the airport's functionality. Central to the effort is the construction of a new terminal lobby and ticketing hall expansion, which involves reconfiguring the central terminal core with additional vertical space, new structural framing, and large-span roof trusses. This lobby incorporates high-performance glazing systems for natural light, post-tensioned concrete slabs for uninterrupted floor plates, and advanced mechanical systems to handle the increased foot traffic. The new hall connects seamlessly to both the south and north concourses, forming a unified passenger circulation loop. One of the largest structural packages nearing completion by 2026 is the satellite concourse expansion. Built with steel framing and deep foundation systems, the expanded concourse adds dozens of new gates equipped with modern boarding bridges, energy-efficient HVAC systems, and wide passenger hold rooms. Each gate is supported by a modular utility backbone that includes data cabling, potable water, and baggage handling extensions. The floor assembly utilizes composite steel decking with concrete topping slabs, designed to support both passenger loads and integrated seating, charging stations, and wayfinding systems. Adjacent to the terminal is the new hotel development, a significant vertical addition to the campus. This high-rise structure is built using reinforced concrete cores and shear walls to provide lateral stability against wind and seismic forces. The hotel, which is on schedule for full interior completion by 2026, is directly connected to the terminal via a covered pedestrian bridge and includes amenities such as conference rooms, restaurants, and observation decks overlooking the airfield. Mechanical plant systems are located on rooftop penthouses, concealed by architectural screening, and are supported by a network of steel beams and slab-on-metal deck construction. On the airside, airfield reconfiguration and apron expansions are underway to support the added gate capacity. This includes new concrete paving slabs poured in large contiguous sections with dowel baskets, expansion joints, and embedded lighting. Jet fuel hydrant systems are integrated beneath the apron surface, supported by trench access points and utility vaults. Stormwater runoff is controlled by a series of trench drains and retention basins designed to meet FAA environmental compliance standards. Ground transportation infrastructure is also being upgraded as part of the BNA Vision, with new roadways, parking garages, and shuttle facilities. These structures are built using precast concrete panels and post-tension beams for fast-track assembly. Intelligent transportation systems are embedded into the structure, with real-time occupancy sensors, automated ticketing systems, and dynamic signage. Let's travel over to Chicago, Illinois, where the O'Hare 21 terminal expansion is redefining the future of air travel in the United States. Being one of the busiest national airports, O'Hare International Airport is undergoing a transformative $8.5 billion modernization initiative, with the Terminal 5 expansion serving as a pivotal component. The expansion of Terminal 5 is designed to address the increasing demand for both domestic and international air travel. By enhancing capacity and integrating state-of-the-art facilities, the project aims to improve passenger experience, operational efficiency, and maintain the status of O'Hare as a global aviation hub. Completed in early 2023, the Terminal 5 expansion added approximately 350,000 square feet to the existing structure, increasing the capacity of the terminal by 25%. This expansion includes 10 new gates, 9 of which utilize multiple aircraft ramp system gates, allowing flexibility to accommodate both wide-body and narrow-body aircraft. The project also involved the renovation of 750,000 square feet of existing space, enhancing passenger amenities by 75%. Key improvements include a reconfigured international arrivals facility, expanded customs and security checkpoints, and a complete overhaul of the baggage handling system. With a total investment of $1.3 billion, the Terminal 5 expansion is part of the broader O'Hare 21 program. This modernization effort is expected to generate substantial economic benefits, including job creation during construction and increased capacity to support future air traffic growth. The project employed advanced construction techniques to minimize disruptions and enhance sustainability. Notably, the design incorporates 40,000 square feet of high-performance glass, water-efficient fixtures exceeding sustainable airport manual requirements, and new Energy Star roofing. The vaulted ceilings and open design of the terminal allow natural light to permeate the space, reducing energy consumption and creating a welcoming environment for travelers. In addition to structural enhancements, the Terminal 5 expansion includes a significant cultural investment. A $3.5 million public art program, the largest single acquisition of works by local artists in Chicago in 30 years, features installations throughout the terminal. These artworks celebrate the diverse communities of the city and provide travelers with an enriched cultural experience. Furthermore, a new 6-story parking garage is under construction, set to open in October 2025. This facility will more than double the available parking at Terminal 5, accommodating the anticipated increase in passenger volume. In Central Ohio, the Intel Ohio Semiconductor Campus, Phase 1, is one of the most closely watched industrial megaprojects tied to the United States manufacturing build-out in the second half of the decade. It is designed as the first stage of a large semiconductor production complex near Columbus, with Phase 1 centered on 2 leading-edge chip fabrication plants and the extensive support infrastructure required to operate them. In any 2026 completion discussion, this project has to be described as a major construction and delivery milestone rather than a simple fully finished campus, because semiconductor facilities are completed through overlapping stages of shell construction, utility activation, clean room installation, equipment move-in, and production ramp. Phase 1 is significant because a semiconductor fab is not only a large building, it is a highly controlled, industrial system made up of clean rooms, vibration-managed foundations, chemical delivery networks, water treatment systems, power distribution equipment, air handling systems, process piping, backup systems, and security-controlled production space. The visible structures are only one part of the build. Much of the project's complexity is in the hidden technical infrastructure that allows fabrication tools to operate within extremely strict environmental tolerances. The construction work associated with reaching key 2026 milestones is concentrated on finishing the main fab structures, closing the building envelope, completing mechanical and electrical plant systems, and pushing the site from heavy civil work into interior technical fit-out. By that stage, work includes structural steel and concrete completion, where still ongoing utility corridor development, substation and power infrastructure advancement, installation of water and wastewater systems, process piping, HVAC systems, cleanroom framing, raised floor systems, filtration equipment, and the commissioning of support buildings that serve the fabs. Exterior works also remain important, including internal roads, drainage, logistics areas, and the site-wide infrastructure needed for a campus that is expected to expand in later phases. A critical distinction for semiconductor projects is the difference between construction completion and operational readiness. Even if major building work reaches an advanced state in 2026, that does not automatically mean full chip production begins immediately. After the physical facilities are largely complete, there is usually a long sequence of cleanroom certification, systems balancing, contamination control verification, specialty equipment installation, tool hookup, process testing, and early production qualification. That means 2026 is best understood as a year of major physical completion and systems transition, for Phase 1, with final industrial readiness, depending on how quickly the project moves through commissioning and tool installation. Just north of Miami's urban core, the Moa Aventura South development is, in 2026, an active mid to high-rise residential construction project shaped by tight site logistics, flood resilience requirements, and the demand for transit-adjacent housing near one of the region's busiest retail and employment centers. In the Miami area megaproject context for 2026, its scale comes from the combination of vertical density, structured parking, and the infrastructure needed to deliver a modern multifamily building in a coastal environment. Construction in 2026 is typically focused on moving the building from structural completion into enclosure and interior delivery. The reinforced concrete frame and central core drive the schedule, with crews completing floor plate pours, stair and elevator cores, and post-tensioning sequences that keep the structure advancing on a predictable cycle. As floors are completed, the facade package follows, with window wall and balcony systems installed to create weather-tight zones that allow interior trades to start work without waiting for the whole tower to top out. Because South Florida construction is defined by rain and humidity, 2026 work includes aggressive waterproofing and moisture management detailing. That shows up in balcony edge treatments, slab penetrations, window interfaces, and podium transitions, where leaks often originate if detailing is rushed. Roofing systems and parapet work also begin earlier than in drier climates, because creating protected interior zones accelerates the overall schedule. Mechanical and electrical work expands rapidly in 2026 as enclosed levels become available. Contractors install vertical risers, corridor duct mains, and fan coil or VRF distribution, depending on the design. Fire protection piping, alarm devices, and stair pressurization systems are installed early because they tie directly to life safety inspections. Electrical distribution grows floor by floor with panel boards, metering, and backup provisions for critical systems like fire pumps and emergency lighting. Podium and parking structure work is a major component in 2026. Many Aventura area multifamily projects use structured parking to reduce land consumption, so construction includes ramp slabs, ventilation, and fire separation between parking and residential floors. Access control systems, entry gates, and camera infrastructure are typically embedded at this stage, along with the conduit network for EV charging capacity, which is increasingly standards. In new developments, interior build-out becomes the dominant activity by mid to late 2026. Crews move through framing, insulation, drywall, and finish trades in a production sequence that prioritizes lower floors first. Unit kitchens and bathrooms drive scheduling because they require coordinated plumbing, rough-ins, waterproofed wet walls, and inspection-ready assemblies before tile and fixtures can proceed. Common areas and amenity spaces are also being built out in 2026, including fitness rooms, co-working areas, and resident lounges that require more complex electrical and HVAC zoning than typical corridors. Site and streetscape work continues in parallel. In 2026, contractors finalize sidewalks, landscaping, and stormwater systems, including on-site retention and controlled discharge required for heavy rain events. Driveway tie-ins, rideshare drop-off geometry, and service access routes are completed with a focus on separating resident traffic from deliveries and waste handling. By 2026, Brightline West has shifted from a proposal into a full-scale Nevada megaproject defined by earth-moving, structures, and systems planning along the I-15 corridor. The project is designed to create a dedicated high-speed rail link between Las Vegas and Southern California, using grade-separated passenger rail infrastructure built for sustained high speeds and frequent service. Construction activity visible in Nevada in 2026 is concentrated around the Las Vegas Valley approach and the corridor's major structure zones. Crews are advancing right-of-way preparation, clearing and grading embankments, and building the subgrade that will carry ballastless track or slab track segments in the higher speed areas. Where the alignment crosses local roads and drainage corridors, 2026 work includes bridge abutments, pier foundations, and precast girder placement to keep the rail line fully separated from traffic. Station development is another major 2026 focus. The Las Vegas terminal site is being prepared with deep utility relocations, foundation work, and early vertical framing for passenger areas and platform structures. This phase also includes the less visible but critical backbone systems, traction power planning, feeder routes, and spaces for substations that will convert and distribute electricity along the line. As these power sites are finalized, contractors install duct banks, conduit runs, and equipment pads that must be in place before rail systems can be energized. Rail systems work ramps up through 2026 in parallel with civil construction. Signal and communications contractors are installing cable routes, equipment rooms, and mounting points for wayside hardware. Because high-speed operations rely on precise train control, this stage is about building the physical network that will later support automated protection, dispatching, and continuous monitoring. Along windy desert segments, teams also implement sand and drainage mitigation, including channel improvements, erosion control, and protective barriers that reduce the risk of drift material accumulating near the track. A defining feature of 2026 construction is sequencing around access and safety. Much of the alignment runs within or adjacent to freeway right-of-way, so the work plan is built around traffic management, night closures, and stage construction zones. Heavy haul deliveries, concrete pours, and crane picks are scheduled to minimize disruption while maintaining steady progress on structures and guideway elements. Timeline-wise, Brightline West has been framed as a late 2020s delivery, with the most frequently discussed target being service in 2028, assuming civil works, systems integration, and testing proceed without major delays. For a project of this type, 2026 is the year that locks in the schedule. If the alignment's major structures, station shells, and power readiness milestones stay on track, 2027 becomes the transition into full track installation, electrification, and corridor-wide testing. In 2026, several major extensions of the Bay Area Rapid Transit System are under construction, forming a critical part of Northern California's long-term transit infrastructure strategy. The largest and most technically complex is the Silicon Valley Phase 2 extension, a 6-mile expansion of BART service from Berryessa, North San Jose, to downtown San Jose and Santa Clara. This project is being led by the Santa Clara Valley Transportation Authority in partnership with BART and is a federally funded multi-billion-dollar endeavor. Construction in 2026 is fully active along the entire Phase 2 alignment. The project includes 4 new stations: 28th Street, Little Portugal, downtown San Jose, Diridon, and Santa Clara. Approximately 5 miles of the alignment will be constructed using a single-bore tunnel, 45 feet in diameter, making it one of the largest subway tunnel sections in North America. In 2026, tunneling operations are scheduled to begin following completion of launch shaft excavation and assembly of the tunnel boring machine. Shaft construction and staging zones are already established at multiple sites, including the western portal near Diridon Station. The downtown San Jose station, which will be built underground, presents specific challenges due to its depth and proximity to active utilities, heritage buildings, and seismic zones. In 2026, deep excavation, support of excavation walls, and early concrete pours are underway. Similar substructure work is progressing at 28th Street and Diridon, where retained cut and mined station boxes are being constructed. Cut and cover methods are being used at the Santa Clara station, which will serve as the new western terminus of the extension and will include a surface-level tail track and storage tracks. The entire Phase 2 extension is projected to open for revenue service by 2036, with major civil work and tunneling expected to conclude by the early 2030s. The project's integration with existing transit hubs, including Caltrain, Amtrak, VTA Light Rail, and future California High-Speed Rail at Diridon, is a key element of the design. In 2026, intermodal design coordination is ongoing between BART, VTA, Caltrain, and city agencies to synchronize platforms, vertical circulation, and fare systems. Elsewhere in the Bay Area, BART is continuing with other network improvement projects in 2026. This includes planning and pre-construction for the potential extension to Livermore along the I-580 corridor. Although not yet in full construction, right-of-way acquisition and environmental reviews are active. This corridor is intended to close a critical gap between Dublin, Pleasanton, and the Tri-Valley region. Throughout Central and Southern California, in 2026, university campuses are undergoing large-scale construction to accommodate rising enrollment, research expansion, and updated sustainability mandates. These developments span multiple University of California and California State University institutions, with a focus on housing, laboratories, medical infrastructure, and renewable energy integration. At the University of California, Merced, construction continues on multiple academic and housing facilities under the 2020 Project Phase 2, expanding the campus's capacity well beyond its original footprint. In 2026, vertical construction is active on new science and engineering buildings, along with residential halls that will add over 1,000 new beds by 2027. These additions support UC Merced's long-term goal to serve over 15,000 students and enhance its research output in agricultural technology and climate science. Set slightly apart from the historic core of downtown Dallas, the Bank of America Tower at Parkside represents one of the most prominent vertical megaprojects under construction in the Dallas region in 2026. Rising within the Park District near Clyde Warren Park, the tower is positioned as a next-generation commercial office building designed to consolidate major corporate operations while redefining the northern edge of the central business district. The project consists of a high-rise office tower with a large floor plate, advanced building systems, and integrated public realm improvements. It is designed to accommodate a single major anchor tenant while also supporting multi-tenant flexibility. The structure replaces older, lower-density development, reflecting a shift toward taller, more efficient office buildings in Dallas's core employment zones. By 2026, the Bank of America Tower at Parkside is firmly in its vertical construction phase. Structural framing dominates activity throughout the year, with reinforced concrete cores and post-tensioned floor slabs rising steadily above street level. Tower cranes remain on site through most of 2026 to support formwork, rebar placement, and concrete pours as the building progresses floor by floor. Facade installation becomes a major focus during 2026. Curtain wall systems, consisting of high-performance glass and metal panels, are installed from the lower levels upward as the structure tops out. This work is carefully sequenced with interior construction to allow mechanical and electrical rough-ins to follow closely behind the enclosure of each completed floor. The facade is engineered for solar performance, glare reduction, and long-term energy efficiency. Interior construction accelerates significantly during 2026. Mechanical, electrical, and plumbing systems are installed across multiple levels simultaneously. This includes high-capacity HVAC systems designed for dense office occupancy, advanced air filtration, and smart building controls. Electrical infrastructure includes redundant power distribution and backup systems consistent with large financial and corporate tenants. Elevator installation is another critical task, underway in 2026. High-speed elevator shafts are completed within the concrete core, followed by cab installation, guide rails, and control systems. These systems are designed to minimize wait times while serving a tall structure with large floor plates and high daily occupancy. Ground level construction remains active throughout 2026 as well. The tower integrates structured parking, loading docks, and secure service access beneath and adjacent to the building. Streetscape improvements, including widened sidewalks, landscaping, and pedestrian connections to nearby parks and transit routes, are constructed alongside vertical progress. These elements are coordinated with city infrastructure upgrades to minimize disruption in a dense urban environment. Life safety systems are installed and tested in phases during 2026. Fireproofing, sprinkler systems, smoke control, and emergency power infrastructure are integrated as each floor reaches substantial completion. These systems must be commissioned incrementally to support ongoing construction above occupied or enclosed levels. From a scheduling perspective, 2026 represents the midpoint to late middle phase of the project timeline. Structural topping out is expected either during or shortly after 2026, depending on sequencing and weather conditions. Once the structure is complete, focus shifts more heavily toward interior finishes, tenant build-outs, and systems commissioning. Major construction activity continues into 2027, with interior finishes, lobby construction, exterior plaza completion, and final facade detailing extending well beyond the structural phase. Testing and commissioning of building systems, including elevators, HVAC, and security systems, are expected to continue through late 2027.
The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, this 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, it's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.
Stretching across agricultural fields and transportation corridors in California's Central Valley, the Hanford Viaduct is one of the most prominent elevated structures in the state's high-speed rail program. Designed to carry future high-speed trains over highways, irrigation canals, and local roads, this viaduct exemplifies long-span bridge engineering on a linear infrastructure scale. Extending more than 6,000 feet in length, the structure is a major part of the route connecting the cities of Bakersfield and Merced. By 2026, substantial portions of the viaduct's superstructure and supporting piers are scheduled for full completion, marking a key advancement in California's effort to build the nation's first dedicated high-speed rail system. Construction began with foundation work on deep pile supports, essential for distributing loads through the soft valley soils and into more stable substrata. Each pile cap anchors groups of cast-in drilled hole piles, some reaching depths of over 100 feet. These piles were installed using large rotary drilling rigs, followed by steel cage placement and concrete pours using tremie methods to avoid soil intrusion. Reinforced pile caps were then formed and cast to support vertical columns rising in pre-engineered intervals along the structure's path. The viaduct's columns are typically cast in place, reinforced concrete shafts with integrated rebar cages designed to resist bending and shear forces from seismic events. Column heights vary based on topography and the elevation required to clear existing obstacles, such as State Route 198 and other major infrastructure. Formwork systems were employed in a climbing sequence, allowing successive concrete pours to build up each column in increments. Once cured and post-tensioned, these columns were capped with pier tables, forming the intermediate support points for the superstructure. The superstructure itself consists of precast concrete girders installed using balanced cantilever construction techniques. Segments were fabricated at a dedicated casting yard, then transported to the site via specialized haulers. Large capacity cranes and launching gantries were used to lift and position these segments atop pier caps, where they were aligned and post-tensioned together with steel cables. This method minimized on-site curing time and allowed for faster assembly across long spans without requiring extensive scaffolding or temporary shoring in active roadways or sensitive environmental zones. Bridge deck construction followed closely behind girder placement. Deck slabs were cast in place atop the precast segments using slip-form paving machines and high-strength concrete mixers designed for thermal resistance and structural integrity. Expansion joints, shear connectors, and deck drainage features were integrated into the pour sequence. Parapet walls and safety barriers were cast with embedded conduit for future rail electrification and signaling systems. By 2026, The entire structural assembly of the Hanford viaduct, including all columns, girders, and deck sections, is expected to be completed, enabling future track installation and system outfitting. This milestone signals the transition from heavy civil construction to rail-specific phases such as ballastless track slab installation, overhead contact system erection, and control system integration. Next up, we have to talk about the Portal North Bridge in New Jersey, a transformative infrastructure project set to redefine rail travel along the Northeast Corridor. The Portal North Bridge is a critical component of the broader Gateway program, aiming to enhance the reliability and capacity of the rail network between Newark, New Jersey, and New York City. The existing Portal Bridge, a 114-year-old swing-span structure over the Hackensack River, has long been a bottleneck, causing frequent delays due to its age and design limitations. The new bridge will replace this outdated infrastructure with a modern, fixed-span bridge, eliminating the need for openings to accommodate maritime traffic. This will significantly improve service reliability for both Amtrak and NJ Transit commuters. The project involves constructing a 2-track, fixed-span bridge rising 50 feet above the Hackensack River, allowing uninterrupted rail service while accommodating maritime navigation beneath. Spanning nearly 2.5 miles, the bridge will feature 3 massive tide arch spans, each weighing approximately 5 million pounds. These arches are being assembled off-site and transported via barge to the construction site for installation. The design eliminates movable components, reducing maintenance needs and enhancing operational efficiency. With a total project cost of approximately $2.3 billion, the Portal North Bridge represents a significant investment in the regional transportation infrastructure. Funding sources include federal grants, state contributions, and investments from Amtrak. The project is expected to generate substantial economic benefits, including job creation during the construction phase and improved connectivity that supports regional economic growth. The construction employs advanced engineering techniques and heavy machinery to handle the massive components involved. The tide arch spans are assembled at a fabrication facility and transported to the site using specialized barges. Heavy lift cranes and other equipment are utilized to position and secure these arches onto the bridge piers. The project also involves constructing deep foundations, retaining walls, and approach structures to integrate the new bridge seamlessly into the existing rail network. For now, the project has achieved significant milestones, with the final arch installed and overall construction approximately 80% complete. The bridge is on track for the first set of tracks to become operational in the second half of 2026, with full project completion anticipated by 2027. These developments mark a significant step forward in modernizing the Northeast Corridor and enhancing the reliability of rail service for hundreds of thousands of daily commuters. Rising on the south shore of Lady Bird Lake, Waterline Tower is one of the most prominent high-rise construction projects associated with Austin's late 2020s development cycle, and in a 2026 context, it stands out as a project moving through the final stages required to convert a super tall structure into an occupied mixed-use building. The development combines residential, hotel, office, retail, and parking functions in a single vertical complex, making it more than a conventional apartment tower or office building. Its significance comes from both height and program density. It is designed to concentrate several major urban uses into one structure at a key downtown site, directly tied to the growth of Austin's skyline and central business district. The project's construction profile is defined by the demands of a very tall, reinforced concrete and steel high-rise built in a constrained urban environment. Earlier phases focus on excavation, foundation work, podium construction, vertical structural progression, floor plate formation, and the coordination of elevators, mechanical risers, and core systems. by the time a project like this enters the 2026 completion window. The central task is no longer simply adding height. The emphasis shifts to enclosure, systems activation, interior build-out, facade completion, and the commissioning work needed for each separate use within the tower. For a project approaching completion in 2026, the most important construction activities during that year would include finishing the curtain wall and exterior skin, completing waterproofing and roof assemblies, finalizing elevator installation and testing, and continuing the mechanical, electrical, plumbing, and fire life safety fit-out across the tower. Interior work becomes the dominant effort. Residential levels require unit completion, corridor finishes, life safety certification, and amenity installation. Hotel floors require guest room build-out, back-of-house systems, kitchens, service circulation, and hospitality-specific commissioning. Office components require lobby completion, vertical transportation readiness, tenant infrastructure, and the handover conditions needed for interior occupancy or later tenant improvements. Ground-level retail areas also move toward storefront completion, utility connection, and public access readiness. Another defining feature of a mixed-use tower like Waterline is that completion does not occur as one simple moment. Different parts of the building can move toward turnover on different sequences. Parking and base building systems may be ready before hotel interiors. Residential units can complete in batches. Retail shells may be delivered before tenant-specific fit-outs. Because of that, 2026 should be understood as the year of final construction execution and phased readiness rather than a single identical completion milestone for every component. In practice, this means the project's schedule is shaped by inspections, testing, punch list correction, systems balancing, facade closeout, and occupancy approvals as much as by visible structural work. High above downtown Miami's core, the Waldorf Astoria Miami is being built in 2026 as a vertically stacked luxury tower where hotel operations and branded residences share one structural and mechanical system. The project's defining feature is its stacked cubes, massing, and that geometry drives the construction approach because each offset volume changes load paths, facade transitions, and floor plate layouts. In 2026, the construction work is centered on three overlapping priorities: pushing the concrete superstructure upward, enclosing the building with curtain wall, and installing the systems that allow hotel and residential spaces to function as separate operational zones. The reinforced concrete core typically leads the schedule, climbing ahead of the floor slabs so elevator shafts, stairwells, and riser corridors stay on pace. Floor-by-floor cycles in 2026 focus on rebar placement, post-tensioning, slab pours, and edge form detailing at the cube offsets, where geometry changes demand tighter survey control and additional structural coordination. Facade installation is a second critical track in 2026. Curtain wall panels are set on the lower and mid levels to make completed floors weather-tight, allowing interior trades to work behind the facade while structure continues above. Miami's wind and rain exposure makes waterproofing and pressure equalization detailing a major part of 2026 work, especially at the stacked transitions where facade lines break and restart. Window wall interfaces, balcony edges, and podium connections receive additional sealing, drainage routing, and inspection cycles to reduce long-term water intrusion risk. Mechanical and electrical work expands rapidly during 2026 as more floors become accessible. Hotel levels require high-capacity ventilation, laundry, and kitchen exhaust pathways, and robust domestic hot water systems, while residential floors demand quieter distribution and separate metering strategies. That separation shows up in 2026 as distinct mechanical rooms, dedicated shafts, and controlled access service corridors being framed and roughed in. Fire protection piping, smoke control systems, and stair pressurization are installed early because they tie directly into life safety approvals and commissioning. Vertical transportation is another major 2026 focus. Elevator rails, machine room installations, and hoistway finishing are sequenced in zones so testing can begin in lower sections while upper floors are still under active construction. For a mixed-use luxury tower, elevator grouping and access control are built into the core planning, so 2026 includes substantial low-voltage work for security, destination dispatch systems, and building-wide communications backbones. Podium and public-facing components also progress in 2026. Lobby volumes, drop-off areas, and back-of-house logistics spaces are built to handle hotel peak loads without interfering with residential circulation. Premium amenities such as elevated decks and spa or pool infrastructure require heavy waterproofing assemblies, structural supports for concentrated loads, and early mechanical tie-ins for filtration and climate control. The Los Angeles Metro D Line Extension, formerly known as the Purple Line Extension, is a $9.3 billion mega project that is carving through some of the busiest, most congested corridors in California. This 9-mile westward expansion of heavy rail is unfolding in 3 carefully staged phases, each one bringing new connectivity to the city's west side. Construction began in 2014, and as of 2026, 2 of the 3 segments are deep in advanced construction, while the third is fully underway. The first section, stretching 3.92 miles from Wilshire Weston to Wilshire La Cienega, was scheduled for completion in 2025. Tunneling for this segment was completed in 2021, with station construction and systems installation now in final phases. Crews are outfitting stations with electrical, ventilation, and communication systems, while surface-level integration work continues at key intersections. The second segment, running from Wilshire, La Cienega to Century City, adds another 2.59 miles of dual-bore tunnel. This phase includes the construction of 2 stations, Wilshire, Rodeo in Beverly Hills, and Century City, Constellation. By 2026, excavation is complete and station interiors are progressing, with structural, mechanical, and architectural elements being finalized. This portion of the line is projected to be operational in 2026. The final segment, extending 2.56 miles to the VA hospital in Westwood, is scheduled for completion in 2027. Tunneling began in 2021, with both tunnel boring machines reaching the Westwood UCLA station box by mid-2024. By 2026, structural work at both Westwood stations is active, including excavation, waterproofing, and concrete shell construction. This third phase is particularly complex, not only due to proximity to critical federal and medical infrastructure, but also because of seismic design considerations near the Santa Monica Fault. All 3 phases are being constructed simultaneously to streamline delivery, maximize cost efficiency, and align operational readiness. Together, they form a continuous underground transit spine linking downtown Los Angeles to Beverly Hills, Century City, and Westwood, some of the region's highest density employment and residential zones. When complete, the D-Line extension will connect riders to major institutions, including UCLA, Cedars-Sinai Medical Center, and a cluster of Fortune 500 offices in Century City. By the time the full extension opens in 2027, the D-Line will operate across 13 miles from Union Station to the VA hospital in Westwood, serving nearly 80,000 weekday riders. This will dramatically reduce commute times along the corridor, potentially cutting rush hour trips from over an hour by car to under 30 minutes by rail. In addition to relieving pressure on the 10 and 405 freeways, the D-Line will improve access to key transit interchanges, including connections with the B-Line, E-Line, and multiple local and express bus routes. In 2026, deep excavation work is underway in the heart of California's rugged Diablo Range. At the core of this activity lies the Pacheco Pass tunnels, 2 parallel bores that will become the most technically demanding segment of the state's high-speed rail system. Spanning approximately 13.5 miles between the Central Valley and the Santa Clara Valley, this tunnel system is being designed to support trains traveling at speeds up to 220 miles per hour. Once complete, it will form the primary mountain crossing linking the Silicon Valley to the rest of the California high-speed rail network. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the Stadium Bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero Power Station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction, with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero Power Station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the megaproject's economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places.
In the expanse of the Texas Panhandle, the Sanford Dam plays a pivotal role in regional water management and flood control, particularly as it impounds Lake Meredith on the Canadian River. Originally constructed in the early 1960s, the dam was designed as an earth-fill embankment with a concrete spillway, serving the dual purposes of municipal water supply and mitigating downstream flooding. Over time, the infrastructure aged, prompting a phased rehabilitation effort aimed at enhancing safety, structural resilience, and operational efficiency. By 2026, significant structural upgrades and instrumentation installations are scheduled for completion, focusing on both the dam body and the outlet work system. One of the central aspects of the modernization program involves strengthening the earthen embankment, which spans nearly 7,000 feet in length and rises over 100 feet above the original riverbed. Crews began by performing extensive geotechnical investigations, including borehole sampling and soil stability analysis, to identify zones of potential seepage or differential settlement. Based on these findings, filter and drain systems were redesigned. A new chimney filter composed of well-graded sand and gravel was installed internally, sandwiched between impermeable clay cores and the outer embankment shell. This redesign allows any infiltrating water to be safely collected and discharged, significantly reducing the risk of piping failure. The downstream slope was regraded and armored with riprap composed of heavy angular rock to guard against erosion from rainfall and potential overtopping. In conjunction with this, tow drains and relief wells were refurbished or newly constructed to relieve hydrostatic pressure and to provide observable points of seepage monitoring. Construction sequencing was carefully managed to maintain reservoir capacity and dam integrity, with earth-moving equipment operating in staged zones and GPS-controlled graders ensuring design specifications were met. The spillway system, originally cast in reinforced concrete and located near the left abutment, underwent its own set of enhancements. Cracking and scaling on the spillway crest and chute surfaces were repaired using epoxy injection and shotcrete overlay techniques. Expansion joints were replaced with water stops designed to accommodate thermal movement while maintaining water tightness. New aerators were installed within the chute profile to minimize cavitation damage under high flow conditions. The stilling basin at the spillway's toe was also restructured with improved energy dissipation blocks and reinforced apron slabs. Another major element reaching completion by 2026 is the modernization of the outlet works. The original gated conduits and control valves were replaced with stainless steel slide gates operated by hydraulic actuators housed within a new gate chamber structure. This upgrade improves flow regulation, allowing more precise water delivery to downstream users. New access galleries were constructed for maintenance and inspection, and redundant power supply lines were routed to ensure system operability during electrical outages. A comprehensive instrumentation network was added throughout the dam structure and appurtenant works. Vibrating wire piezometers, inclinometers, and settlement plates were embedded at key points to monitor pore pressure, movement, and subsurface changes in real time. These data feeds are linked to a centralized supervisory control and data acquisition system, which supports predictive maintenance and emergency response planning. The Helen Diller Medical Center at the University of California, San Francisco, is one of the most advanced medical facilities ever built on the West Coast. Located at Parnassus Heights, this $4.3 billion megaproject completed in 2026, stands as a fusion of cutting-edge healthcare, seismic engineering, and smart infrastructure. The University of California is a global leader in research and medicine, yet its aging hospital buildings were outdated and not up to the seismic safety mandates of California. With the state requiring all acute care hospitals to meet specific seismic regulations by 2030, UCSF acted early, building a structure that not only meets but exceeds the toughest standards for seismic resilience. At the heart of the facility is a 15-story medical tower with over 300 patient beds, 24 operating rooms, and expansive ICU and trauma units. It is designed to withstand a magnitude 8.0 earthquake, using base-isolated foundations and energy-dissipating steel bracing. This will allow the building to sway gently during seismic activity, minimizing damage and keeping operations running even in a disaster. The construction process was a feat of logistics. With limited space on the Parnassus Heights campus, contractors used vertical staging, off-site modular fabrication, and just-in-time material delivery to keep the site efficient. Tower cranes, robotic arms, and BIM software synchronized every phase, ensuring equipment installation, utility routing, and wall systems were aligned down to the inch. One of the standout features is the smart infrastructure of the facility. Every patient room includes real-time monitoring systems, adaptive lighting, and AI-powered diagnostic support terminals for clinicians. These systems communicate with the central data network of University of California, San Francisco, allowing remote specialists to consult in real time and reducing diagnostic errors by up to 30%. Sustainability was also a core pillar. The building meets LEED Platinum standards with solar panels, grey water recycling, triple glazed windows, and active chilled beam HVAC systems that cut energy consumption by 45% compared to traditional hospitals. The exterior features aluminum sunshades and vertical gardens that reduce solar gain and improve patient well-being. From a machinery standpoint, the project utilized automated concrete pumps, self-climbing formwork systems, and prefab MEP modules. The mechanical, electrical, and plumbing infrastructure of each floor was assembled off-site and hoisted into place like puzzle pieces, cutting installation time in half. Beyond the technology, what makes the Helen Diller Medical Center remarkable is its human-centered design. Large windows, rooftop gardens, calming interiors, and dedicated family spaces were all designed with input from patients, nurses, and doctors, a true reflection of community health priorities. At John F. Kennedy International Airport, one of the most important US megaproject milestones in 2026 is the opening phase of the new Terminal 1, a major redevelopment on the airport's south side in New York. This project is designed to replace the former Terminal 1, Terminal 2, and the site of the former Terminal 3 with a single, much larger international gateway. It is one of the central pieces of JFK's broader airport transformation, and in 2026, the focus is on turning a long-running construction site into an operating terminal environment. The new Terminal 1 is planned as a large-scale international terminal with modern aircraft gates, expanded passenger processing space, upgraded baggage systems, new security screening areas, and infrastructure designed for wide-body aircraft used on long-haul routes. Its importance comes from both scale and function. JFK is one of the main international entry points into the United States, and the terminal is being built to increase capacity, improve circulation, and support a more efficient border, customs, and airline operation than the older facilities it replaces. Construction work leading into 2026 is centered on delivering the first completed section of the terminal. That includes finishing the structural frame and enclosure of the initial concourses, completing interior fit-out, installing mechanical, electrical, and plumbing systems, testing baggage handling equipment, commissioning airfield side systems, and preparing passenger processing zones for operation. road access, curbside works, utility connections, and apron. Infrastructure also need to be completed in sequence, so the first phase can function as a live airport terminal rather than just a finished building shell. A major challenge is that this work is being carried out inside one of the busiest aviation environments in the country. Construction has to be staged around active aircraft movements, existing terminal operations, security restrictions, and strict commissioning requirements. That makes 2026 especially important because the project must shift from heavy civil and structural work into testing, certification, operational readiness, and phase turnover. In airport megaprojects, that transition is often the most difficult part, since systems integration matters as much as the building itself. For a video about US megaprojects completing in 2026, the new Terminal 1 fits best as a project reaching a major completion milestone in that year, rather than its absolute final build-out. The first operating phase is expected in 2026, while the full terminal program continues beyond that initial opening through later phases. That means 2026 is the year when the project begins delivering real passenger capacity, even though additional gates, support areas, and final expansion elements may continue afterward. Across downtown Miami's development pipeline, Ocan Tower is one of the most technically demanding high-rise builds discussed for the 2026 megaproject landscape because it combines a near super tall structure with hotel, residential, and amenity users stacked in a single vertical system. The project's design is defined by a tapered, curving profile that requires non-repeating formwork, tight survey control, and careful coordination between facade geometry and the concrete core. For a tower of this height class, the construction story in 2026 is typically about structure, enclosure, and building systems moving in parallel. Vertical concrete work is the pacing item, with the central core climbing ahead of the floor plates to keep elevators, stairs, and mechanical risers on schedule. High-rise crews cycle through rebar placement, post-tensioning, and slab pours, then immediately follow with perimeter edge forms that lock in the tower's changing shape as it rises. Facade work becomes a second critical path in 2026. Curtain wall panels are installed from the lower levels upward to create weather-tight floors that can transition into interior build-out while structure continues above. Because Miami's climate is humid and storm-prone, 2026 enclosure work includes water management detailing, pressure testing of facade zones, and robust waterproofing around balcony edges, window interfaces, and podium transitions. Mechanical and electrical installation expands rapidly during this phase. In 2026, contractors route chilled water and condenser systems, build out air handling rooms, and install vertical shafts for smoke control and stair pressurization. Electrical distribution grows floor by floor, with switchgear, risers, and backup power pathways installed early to support life safety systems, elevators, and the dense loads that come with hotel operations. Mixed-use towers add complexity because different occupancies have different requirements. In 2026, construction sequencing must separate hotel back-of-house routes from residential circulation while maintaining code-compliant egress and fire separation between zones. That translates into additional rated assemblies, dedicated service elevators, and separate mechanical distribution strategies, all coordinated before finishes can proceed. Amenity and public-facing components also shape 2026 work. Where the tower includes a signature pool deck or rooftop amenity, crews build transfer slabs, waterproofing systems, and structural supports that can carry heavy live loads and mechanical equipment. Street-level podium work, including retail shells and drop-off zones, is usually being fitted out in 2026 as well, with storefront glazing, loading access, and traffic interface improvements installed to support eventual operations.